Okay, I wanted to go over the solutions for today's homework, and we'll probably have time to get started on the practice test, 3 and 4. And if we're going to go over, we'll complete that on Monday. So be sure to have worked through all the problems of the practice test by Monday, so we can finish going over that. And the test itself will be Monday after Thanksgiving. And then we'll have Wednesday of that week following Thanksgiving. We'll go over other parts of the practice fund as well. And then Friday there will be no class. So next week of the week after Thanksgiving. Okay, so by the way, this was I've asked about textbooks for 3550. Some of you are in that class for next semester. So I've decided to use, as I said before, I'm going to use the quantum textbook that you have now. I'm also going to use the mechanics textbook, the first volume. We'll go back over impetus and kinetic energy and those things that you didn't have. I don't think any of you, or very few of you, have had the mechanics, PFR mechanics. So we're going to go over the few topics there, and also special relativity from there. So we'll do entanglement, measurements, a little bit of quantum computing, so you get a flavor of what that's about, and special relativity. And at the end, we'll go over outside of the textbook, we'll go over the standard model of particle physics. So that's not a textbook, but that will be a topic that's outside of the textbook. Oh, yeah, I guess in this one also we'll do measurement, we'll do entanglement. Have more than one entity involved in the system. We've just been doing one particle. So we'll do multiple particles and cover entanglement. We'll cover measurement. Also, we'll cover Lagrangian. Because that's really the heart of the empiriometric in modern physics, is the Lagrangian. We'll use the Lagrangians as the standard model when we talk about standard model. Okay, so we're considering now what happens to a hydrogen atom in the presence of a magnetic field. So I'll call H naught is the Hamiltonian for just the hydrogen atom by itself. So it's the kinetic energy operator minus the potential, which looks like that. And we studied the solutions for this time independent Schrodinger equation. So these states are eigenstates of that operator, and the eigenvalues, the energy for that state. The energy just depends on the n quantum number, the principal quantum number. And these states are composed of products. They're a function of r, a function of theta, and a function of phi using spherical coordinates, and we combine these together, typically to be just a function of two angles. And we argued, it showed how we have two operators that can use this Hamiltonian. And also each other. Operators relating to the angular momentum. And so these states are then eigenstates of all three operators, the Hamiltonian and also the angular momentum operators. This M here, remember, is the quantum number. You'll see here in a minute why it's called the magnetic quantum number. The quantum number associated with the phi. There's a part here in this function, which is EI and phi. So that quantum number, that little m there is not mass. It's one of the three quantum numbers describing states. So all of the eigenstates of the hydrogen atom can be described by these three quantum numbers, and L and M. And we showed how, for example, n equals 1, at both L equals 0 and n equals 0, called 1s, n equals 2, 2s, or P, and n equals 3. These combinations, these possibilities. So this was the 3s, the 3p, and the 3d. So among the S states, there's just one S state. For the P state, there's 3 P states. There's 5 of these states. Okay, so if we place the hydrogen atom in a magnetic field, and we're going to choose our coordinate system so that the z-axis is along the magnetic field. The reason for doing that will be clear here in just a minute. We're free to choose our coordinate system, so we choose a coordinate system along that axis. Then there is an interaction of the magnetic dipole moment with this B field. Go back to electromagnetism, place a current carrying loop inside of a magnetic field. There's an energy associated with the orientation of that magnetic dipole moment with the B field. In the case of a current carrying loop, we have current flowing in a loop like this. The magnetic dipole moment is perpendicular to the loop. And so these states, remember when I showed you the orbits of these states, the electron is orbiting around the z-axis, and so that produces the magnetic dipole moment along the z-axis. Like this, which is proportional to the angular momentum around the z-axis. You can see how it would be greater magnetic moment for higher angular momentum along the z-axis. So we're adding a term then, the Hamiltonian, in the presence of a magnetic field. I guess there's an H bar here, right? No, that's it. Okay. It should be UL. So the strength of this coupling here between the orbital angular momentum and the magnetic field has to be measured, and the value of it can come out of the measurement that we're just looking at. It turns out to be the charge on the electron divided by the mass of the electron. Yes, I guess. Okay. So this is actually a pretty easy problem to solve. We're looking for eigenstates and eigenvalues of this new Hamiltonian, which is the energy of the electron moving around the proton, but also has this interaction with the magnetic field. Put in an E here. Depends on the strength of the magnetic field. If B is 0, then we just get back to the hydrogen atom before, and all everything that I wrote down is follows. But it turns out to be pretty easy to construct the eigenstates of this, because this change in the Hamiltonian is related to the angular momentum in the z direction. So if we apply this to one of these states, see already that this is going to be quite simple, and that's because this change commutes with the original Hamiltonian. So we can, the eigenstates of this are still going to be eigenstates of the new Hamiltonian, but they're going to be shifted. We have to find what happens for the particular state that we're looking at. The momentum depends on M quantum number. That's why it's called the magnetic quantum number. So this then is acting on this state. This is acting on the same state that it was before. So that's just the energy of the electron in that orbital without the magnetic field. And so we get the eigenstates we had before are now still eigenstates in this situation, but the energies are going to be different. They're going to be modified by the addition of this term that depends on the M quantum. So that makes it pretty easy. So the 1s state, then the energy in this perturbed situation, the new energy, is called tilde, in the presence of the magnetic field. N is equal to 0. So there's no shift in the energy of the 1s state. And that's true for any of the s states, 2s, 3s, and so forth. They don't shift. This would be E1. In this case, now this is E2. Those remain the same. Yes, sir.
So in the like the current carrying wire, you have like a vector with M like going perpendicular. Like is M's not mass, is it?
No, that's the magnetic dipole moment.
Okay.
I'm sorry, I'm using this. The symbol M gets used in 3 different places.
Okay, yeah.
Here. Back in E&M, we define the magnetic dipole moment of the current carrying movement. We also have the mass of the electron, and we also have the M quantum number. So all 3 are using the same symbol for 3 different things, which guarantee you trouble. Okay, so let's look at the 2p state then. Now the 3 values for little m. U B H bar plus or 0 or minus U B H bar. So the energy which had 3 p states all at the same energy now gets split by the presence of the magnetic field. So instead of having all the p states have the same energy, now they all have different energy, but this middle one is still the same as 2s. The 3p is similar, same except it's an E3 here. And the 3d now has 5 possibilities. So at the value of E3, we have a 3s state, we have one of the 3p states, we have one of the 3d states. But we get in addition, these states have been split here. So what we had before then, remembering these energies, we had the 1s state, so this is for no magnetic field. We had a 1s state here that was down at 13.6 electron volts, 1 Rydberg down from the reference. Reference, by the way, we should remind ourselves of what is this reference. Where is the energy equal to 0? What kind of situation? goes back to the potential energy. We said the potential energy. Yes. So where is the potential energy zero? Yeah, no, because that would be infinite there. If R goes to zero, this becomes infinite. It's not zero. Where the electron is pulled completely away from the proton. So this zero here, this reference is when the electron is pulled completely away from the proton. It's free of the proton. And so that's the reference. And so this is the amount of energy that would be gained if an electron that was free of the proton fell down into the 1s orbital. Okay, so then we had 1/4 of this, right? The next one, E2 is 1/4 of this up here. And we had 2s and 2p, and there were 3 of these. And then the next one was the 1/9 of this value. We have 3s, 3p, and there are 3 of those, and the 3d, and there are 5 of those. Okay, so in the absence of a magnetic field, you can have transitions, for example, from the 2p down to the 1s. If you could somehow excite an electron in the 2p state. We haven't talked about how these transitions would take place, but further development of the theory will show us then that we can, if we excite an electron up here, it could fall down into the 1s and emit light at this frequency, which is relating to the difference between the 2p. Yeah, that's right. Between 2p and the 1s. So this would be a light which is taking place from because of an electron that falls from one of the 2p levels down to the 1s. And that's generically how all of the hydrogen spectrum is understood in the absence of the B field. You have more states up here. They're crowding up, approaching the zero. All of them can have transitions among each other, but there are certain selection rules that are permitted. So not all states can couple to all states. There are only certain states that are allowed. We haven't covered that. We could look at that next semester, I guess, but you can pretty much understand the generic idea. Okay, so now let's suppose we put on the B field. So what happens to the 1s state? There's one of them. Nothing happens. The energy doesn't shift. It's not shifted by the presence of the magnetic field. What happens to these states? Yeah, you get 2 states, so there are actually 4 at this level. And up here there are 9 here. Okay, so these 4 are split. 2 of them remain the same, but one has gone up and one has gone down by an amount that's proportional to the strength of the magnetic field. In the case of the 3 level, so the middle level, I guess, let's see here. We have the S, 3s, one of the 3p's, one of the 3d's. So there are 3 states in the middle. Then the splitting of the p states is the same as the splitting of the d states here. This splitting. So there are 2 of them here, and here, and then finally the one that's highest or lowest is the d state. So we get a sequence of 1, 2, 3, 2, 1, all adding up to 9. And so if you do this in a controlled environment, you can actually see the splitting happening. Here's how you see the splitting. So we have 2 p states. Remember, there's p states have been split. So now we have a transition from any one of those down to the ground state, down to the 1s. And so now the hydrogen line that corresponded in the absence of a magnetic field is now split into 3 lines. And the splitting is governed by the strength of the magnetic field. So you can determine by looking at the hydrogen atom spectrum the hydrogen is in the presence of the magnetic field. And by having done this in a controlled way, you can actually determine the strength of the magnetic field of a hydrogen atom that's very far away. So this is very useful in astronomy, for example, to measure the strength of the magnetic field at locations wherever we're getting some light coming from it. We can look at splitting and determine the strength of the magnetic field in that location. So this is called the Zeeman effect. And it demonstrates the quantization of the orbits in the hydrogen atom. Very nice experiment, because without the quantization, if you expected that the angular momentum did not have to be quantized, you would expect a broad smear, not discrete lines. So the discreteness of the hydrogen spectrum in the presence of the B field demonstrates the quantization of the orbits of the electron in the hydrogen atom. Yes.
And but we're still talking about like the average for like all the like hydrogen atoms that we or whatever, like the big group of them, that's their average. Because that's not like is it really like the hydrogen atoms has these discrete, like each particular has these discrete ones, so they can't be outside of that? Or?
Yes.
So each individual hydrogen atom has these discrete.
Not each individual hydrogen atom, be one of them. Just as in this case where we say, what does this mean? It means that all members of the ensemble are going to have that energy that's associated with this state. And some of the hydrogen atoms will be in this state, some will be in this state, some will be in that. Those that are in this state will emit light at that frequency, and so forth. So you'll have a cloud, hydrogen cloud, some of them will be in each one of these states. So for the whole gas, we'll get 3 different lines coming out, or 3 different lines being absorbed. There's a reverse process where you shine light on a hydrogen atom, and you can excite it from the ground state up to one of these excited levels. And so you could get the reverse process on the absorption lines. You'll see splitting and the dark lines being absorbed by hydrogen. So for example, the light coming from the sun is passing through a region of hydrogen gas that can absorb light from the sun before it gets to us. So it'll show up as dark lines in the overall bright spectrum light from the sun.
And protons, is this the protons field that's
No.
the experience of matter? Is it just like
It's the magnetic field that the hydrogen atom is in, coming from someplace else. I take in the lab, I just take some gas cylinder, make a magnetic field, solenoid or something, put it inside of a magnetic field, look at the excitation or absorption spectrum. I'm sorry, the emission or the absorption spectrum. Okay, but it turns out that this is not quite so simple. That's a topic we don't have quite time to consider. But the angular momentum of the electron in the hydrogen atom is not simply orbital angular momentum. There's another part to it. So this story is actually a little too simple. So we have the orbital angular momentum. But there's also an internal angular momentum that the electron has, which is not well understood because it has something to do with the internal structure of the electron, which we don't understand very well. But the total angular momentum is a combination of these 2. And so the interaction with the magnetic field actually is more complicated than what I've shown here, because there's also the influence of the spin. And the spin is actually a very interesting topic, and that's where we're going to begin. In the next course in modern physics, we'll start with the electron spin and how to describe the quantum mechanics of the internal angular momentum of the electron. So the electron has a magnetic moment, which comes about from this internal spin. that magnetic moment also interacts with the magnetic field. And it takes a little while to figure out how to describe the quantum mechanics of the spin. And that's an interesting subject for a lot of reasons, because it tells us more about electrons. But the mathematics of the spin of an electron is going to be borrowed in quantum computing. So electron spin, and quantum mechanics of this, borrowed, is commonly used in quantum computing. By quantum computing, I mean the application of quantum mechanics, developing an algorithmic way of using quantum states, systems of quantum mechanical behavior. And so it's very interesting once you understand quantum mechanics of this electron spin at the level that we do. We're also going to take a little foray into quantum computing. We'll see how that works. Any questions about this? Yeah.
I thought. So you do have like, you have like.
Really good. What's going on out there?
Band? I don't know. Or some random dudes.
Random.
Yeah, some random dudes.
Oh. It's a brass band.
Trying to get us energy to help out.
Of course, that's for us. So
Yeah, exactly, yeah.
They're doing that for us.
Well, my question was, so you're saying, I'm trying to understand what that diagram means. And so that's just like a schematic way of doing what we've done. It's like if you plug in, if you make n equal 1 or L equal 1, or that's just like a schematic. It's like a schematic way of looking at it.
I'm just drawing the energy eigenvalues in the presence of a magnetic field and not.
So these are the energy eigenvalues of the Schrödinger equations for the hydrogen atom.
In the presence of a B field.
The presence of the B field. That guy to the left is the presence of a non-considered not.
No B field. And you can put the gas in the magnetic field and turn the strength of the magnetic field up, and you can see these lines split. One bright line becomes 3 lines or 5 lines.
Those lines appear because of like.
Because of the angular momentum causes a magnetic moment in the hydrogen atom. So magnets in relation to the compass effect, right? The compass wants to orient in the direction of the B field with respect to the B field. So each of these hydrogen atoms is a little compass in that sense. It has a magnetic moment that affects the energy, depending on how it's aligned with respect to the B field.
So what's a magnetic moment again? That just means it's like a fake circle, or
No fake about it. And if you take a current carrying loop, that produces a magnetic interaction with a B field. It interacts with the B field. Go back and look up at E&M, PFR QM. I'm interested to review this. Look up magnetic dipoles. There's a corresponding situation with electric dipoles. You have a separation of charge between, say, a plus and a minus. This dipole, this is called an electric dipole. This will then interact within the electric field that's present and produce a change in the energy depending on how this dipole is oriented with respect to the electric field. This is a magnetic analog to that. That's what shows up here.
oh, not moments. I'm sorry.
It's called a moment. Yeah, it's called a magnetic dipole moment.
I don't understand I don't remember what it means by magnetic dipole, but how do you have like a moment of that? exist for a moment?
No. Yeah, no, moment, not in the sense of time, but in the sense of having something extended. So you might remember an angular, the moment of angular,
Moment of inertia?
moment of inertia has to do with a body which has some kind of extension to it. So if it's rotating, the moment has to do with the extension of that body perpendicular to the axis of rotation. That sort of moment.
Oh, so moment in this context means the body has extension. Just like we're not treating it like it's a point, we're treating it like it has extension.
Right. The Earth going around the sun, there's an orbital angular momentum. Could be described as the Earth were charged, it would also produce a magnetic field, a magnetic dipole moment. Okay, so let's start on the practice exam. I guess I should just a little bit of a tease. The angular momentum. Maybe I should say this first. Yeah. Okay. So we see it splits into say 3 or 5 possibilities, with the central one being 0. This kind of splitting a 3-fold state gets split, or a 5-fold state gets split like this by the presence of a magnetic field. This is, we're just considering the orbital angular momentum alone. But with the spin, an electron would actually, some of the states would actually split into 2. Rather than 3. Which is a strange thing. There's up and down. Not. So this is the spin part is more mountain. Yes.
Okay, so for like a diagram pad, you have loops.
Yeah.
If we pick one loop that has it's going to generate a magnetic field, does that not have an effect on other loops? Do those loops not affect that initial loop that we picked?
Well, those different orbits, remember, are different members of the ensemble. They're not present to each other. All the members of the ensemble are separate. But if you get a hydrogen gas, there will be a interaction among the hydrogen atoms because of their magnetic moments. That's pretty weak, but it's there.
Okay.
Depends on the density of the gas.
Well, so if it has that average, so if the particle has that average orbital, that average orbit from the proton, like that little like ring path it takes, it'll cause like these lights. That's a lot.
Don't do that. They all have the same value of M. I have the picture of the orbits. These were all for the same state. Right? These I just drew several of them. Don't think that these are the M states. They all have the same value of M. This was all for the I guess if I was drawing it for the 2p is n equals 1. So L equals 1, n equals 1 state. All have to have the ensemble, different members of the ensemble will be tracing different orbits, but they all have the same value of M at the same magnetic moment. So don't think when I drew it like this that these are different values of M. They're all the same. Yes, ma'am.
In chem, whenever you say the spin is +1/2 or -1/2, does that have any real significance?
Yeah.
Or, like, what is that?
So we found for orbital angular momentum that L had to have integer values. Those are the allowed values of L. And then we said for certain values of N, only certain values of L are allowed. But L had to be 0, 1, 2, 3, or 4, and so forth. And then M could be from -L to +L for each one of these. Okay, what we find with spin is that there's a quantum number which is just stuck at 1/2. Instead of L equals equals 0 or L equals 1, there's a quantum number which is at 1/2, which corresponds to L. We have half infinite values. And the values of M now are plus or minus 1/2 associated with that S. So in place of the L quantum number, we have an S quantum number. And that, and again, M can range from minus S to plus S, which just has two values. So the electron has said to have half spin 1/2 particle. Unlike the orbital angular momentum, which can keep going up, the spin of the electron is very narrow value. It's only got a quantum number of 1/2. The spin can either be up or down. So that's an additional factor that we have to take into account. In addition to the orbital angular momentum, there's the spin angular momentum. Total angular momentum is a combination of those two. And so here's the way to work it out. It just takes time. So we're going to start studying spin beginning of the next semester. Okay, so on to the practice test. So the first problem is to write the current. The volume current density, or in this case, it'd be linear current density from the wave function. So I haven't had you memorize this before, but now you should memorize. How to do it.
It was like sine star.
Go ahead. I'm going to let
I apologize.
Mr. Silva do it. I'm going to write it down. Yeah, it's very close. There's just one minor mistake. Does anybody see it? Yeah, there's an I. Oh. So as a way to help your memory on this, try substituting in a plane wave. Try that. That'll help you to remember this, because for this case, K should equal H bar K over M. Yeah. So we substitute plane wave in here. We get minus IK, and then we get a d psi by dx gives an IK. And then we get either the IKX and a minus IK. So this thing inside the square brackets just gives 2IK. Done. And this constant out front, the negative I cancels that I, 2 here cancels 2, so you get H bar K over. So that's how I remember this, by figuring out the combination of terms that gives this result of the plane. Good. Okay, so all right, so let's see, we got the first problem here is the particle of mass M scattering off of a step up. So here's the potential energy, like this. And you're given that the energy of the incoming particles is greater than the step up. Okay. So in effect, you're being walked through the solution. So part A is identify the two regions. Now let's take this divider right here. Maybe we said that x equals 0 here. X 0 right here. The two regions are on the left of the step and above where the step is, the plateau up here. So region 1 and region 2. Right potential in both regions. Do that, it's really easy. Right p of x. So he's combined it to write it in one form. This is the step function u of x. All right, write down the Schrodinger equation in both regions. They have two different equations. Kind of hard to keep writing it like this. Write it down separately for the two regions, region 1 and region 2. You can do that.
Oh, like, what's the context?
This is the context. Right, the time independent Schrodinger equation.
No.
Both regions.
If there's no particles, there's not a Schrodinger equation.
And no particles. The stream of electrons coming in.
Oh, there's a string of electrons coming in.
Yeah.
Okay, yeah. I don't see that.
Particle of mass m coming in from the left, or the energy of the particles coming in. So you're writing the solution. I just want the Schrodinger equation. I am asking, not the solution. That's the part B. I'm just asking for the. You did it right there. That's it for region 1. Now write it for region 2. You're making this too hard. Right. Right. Okay. So write the general form for the wave function in each of these regions. The next step, solve these equations. And you're given that the energy is above this step. Now, this is the equation for a free particle, right? So what's the general solution for a free particle? Yes. Chamber.
I know I'm missing something. Is the case supposed to be specific to that?
To that region, yeah. Call it K1, there you go. Good. Okay. So how does this omega relate to anything? How do we go from these are time dependent solutions, right? Write down the time independent solution. How do we go from the time dependent to the time independent? Say again?
You just take it out.
Yeah, we assume that this exponential dependence on time, use a minus I omega t everything. Right? So the wave function I'm looking for here is the time independent part. The two parts, the right traveling and the left traveling. So this time dependence here has already been factored out to get to this point. And so how does omega fit in? It's the energy divided by h bar. That's that omega.
So would it be like process of further two for more general solution?
Yes, that's right. So we have a right traveling and a left traveling, but there's the strength of each one. We have an incoming wave of some amplitude, which is determined by the setup. We have a reflected part. We have an unknown strength here. Okay, so and now with this K1, how does it relate to the energy? Substitute it into here. You'll see that energy has to equal that. So K1 for 2m d over h bar squared. Okay, so you're on the right track. Just not quite there. That's for region 1. How about region 2? It needs a strength here. Amount that's gotten through and it's traveling to the right. Why is there no corresponding part traveling to the left? Yeah, because there's nothing out here that it can reflect off of. You're sending particles in here. There's no way to make some current coming this way from over here because there's nothing to bounce off. Okay, and how about K2? How does K2 relate to the energy?
That's the same energy relation that replaces with the K2.
Nope.
That would be like addition
Let's solve this equation.
plus the.
Okay, so K2 is not this. seem like a long time ago that we did this. Okay, so then, so we're out of time for today, but the next the next step is to apply the continuity condition. But just very quickly, what is the continuity? Well, it's a little more general. It's the
Wave function will be continuous.
wave function matches itself in the two regions at the place where the two regions connect, and the slope. So this is already continuous and has continuous slope in region 1. This already is continuous and has continuous slope in region 2. What's left is to make sure it's continuous, has continuous value and slope at the interface between the two. Okay. Then from that you get B and C. All righty, so work on these problems for Monday. We're going to do more of this. Going over this, the practice test has variations on the same theme slightly differently. What happens in the interface below the step? All right, see you on Monday.